Okay, in this video I'd like to prove or show what Planck or Max Planck tried to do in terms of describing the Blackbody formula. And initially his attempt was to use continuous energy levels. Or not the Blackbody formula, the Blackbody spectrum. Just to remind people, okay, if you plot energy density versus wavelength or frequency, you're going to get a curve that looks something like this. Alright, and this is one of the things which motivated quantum physics. And Planck was trying to explain this. Alright, and Rayleigh and Jeans tried to do the same thing as well. And his first step was to say, what if we had continuous energy levels? So what he's saying is, for example, you could have 1 unit of energy, you could have 2 units of energy, you could have 1,000,000 units of energy. You could have 1 over 1,000,000 units of energy. In that you could have any level of energy you want. It's like saying, let's say this curve was, we had a linear curve, say that was this line here represents all the energy values you can possibly have. And all you have to do is say, well, I want to have this much energy, or this much, or this much, or this much. And it can have any amount of energy you like. In saying that, it's a continuous level, the energy levels are continuous. So he made this, that was his first guess. Alright, so let's go and see what happens if you use continuous energy levels and try and work out or try and, we'll say, fit this to the Blackbody radiation curve. So the first thing we need to do is find out what the probability of having a certain energy is. So the probability of having a certain energy is proportional to the Boltzmann factor, which we call e to the negative v over kt. Alright, that's the Boltzmann factor. Don't worry about that, just that's kind of a small bit of theory. Just accept that for the moment. So obviously if it's proportional to it, that means it's actually equal to it multiplied by a constant. So we need to work out what this constant is. Now since we're talking about probabilities and energy levels, well, it's got to have some energy. So therefore, if you integrate it over infinity, you're going to get 1. Okay, so obviously it's like saying the probability of a particle being somewhere in space. All you do is integrate it from negative to positive infinity, saying it's got to be somewhere in space, and the total probability must be 1. Okay, because 1 is the highest probability you can get. So, let's do the following. Let us make a substitution. Let x equal to negative v over kt. Notice the negative sign, that's quite important. As a result, dx de is equal to negative 1 over k times t. And we'll say de is equal to negative dx times k times t. Let's apply that to our formula. Okay, what we're trying to do is integrate the probability of finding something being at a certain energy from negative infinity to positive infinity. Okay? Now it's just as easy to integrate it from 0 to positive infinity. Okay? So this probability must be equal to 1 in order for it to be somewhere, or in order not to be somewhere. I'm confusing myself with a bit of particle physics. But anyway, in order for it to have some value, it must have a value somewhere. So let's plug in what we have. That means we're integrating from 0 to positive infinity of our constant times e to the x times negative kt times dx. And that's a pretty straightforward integral, and you're going to get negative c times k times t times e to the x, not x to the x, e to the x, evaluated at 0 and at infinity. Therefore, negative c times k times t is equal to e to the negative infinity, negative e to the 0. This is equal to 1, of course, and this is equal to 0. That's equal to c times k times t, that's equal to 1. Therefore, c is equal to 1 over kt. And we found our constant. Therefore, the probability of being at a certain energy level is equal to e to the negative v over kt over k times t. That's correct. That's the probability of being at a certain energy. So that's the first thing Planck needed to do, and that's pretty straightforward stuff. The next thing he needs to do is plug that into his already proposed Blackbody curve, or Blackbody formula. So Planck had already said that he already thought that the energy density per unit frequency is equal to 8 pi times the frequency cubed over c cubed, or frequency squared over c cubed, times the average energy per unit frequency interval. This is the Greek letter nu, nu. Alright, that's the frequency. That's the frequency. So the next thing we need to do is plug our probability in. Okay, so bear with me one moment. The next thing we know is that the average energy of E continuous is equal to the integral from 0 to positive infinity of the current energy level times the probability of being in that energy level, of course, integrated dE. Alright, so therefore the average energy continuous is equal to, by the way, these angle brackets are the average, the integral of the current energy level that you're looking to find out about, times the Boltzmann factor, divided by kT integrated dE. That looks kind of horrible, but to be honest, it's pretty straightforward stuff. So once again, we're going to make a substitution. We're going to get let x equal to E over kT. This time it's a positive E over kT. Therefore dx dE is equal to 1 over kT. Therefore dx times kT is equal to dE. Therefore E is equal to x times kT. Alright, loads of different ways of writing the same thing. All of those just so we can make this substitution into this integral. So we can say the following. We can say that the average energy, continuous of course, I'm going to imply that from now on, is equal to the integral from from 0 to positive infinity of x times kT times the exponential to the negative x dx. That's going to be equal to kT times the integral again times x times e to the negative x dx. Alright? Now we need to do ourselves a bit of integration by parts. So this is u and this is v. Now people have different ways of thinking about integration by parts. The way I think about it is follows. Well, I just make a small table for myself. I have u, I have du dx. It's not always dx, but I just say it to myself in my head, dv dx and v. And I just fill in the pieces, okay, that I need to. So if you look at this, we're going to get the following pieces. Alright, so basically that isn't u, that isn't v, that's dv. Alright, so that's the way I look at this, and then we know the formula thereafter. We can plug that into the formula for integration by parts. Okay, so bear with me now a moment. You're going to have to remember these, or write them down in your copy if you like, but I'm just going to rub them out because I'm using my notes here. So as a result, the average energy becomes k times t, which was on the outside of course, times the integral. And the integral becomes negative x times e to the negative x. That's all evaluated between 0 and positive infinity, plus the integral from 0 to positive infinity of e to the negative x dx. Close bracket. Alright, so therefore the average energy is equal to kT times negative infinity times 0 minus 0 plus negative e to the negative x integrated between 0 and infinity, and that turns out to be 0 for the same reasons we did in the past. So as a result, you get that the average energy there's something I missed there, I'm after putting in a typo there somewhere, is equal to kT. One of these is 1, e to the naught is 1. Okay, there's e to the naught there. Alright? So e to the naught, that part of that is 1 and part of it is 0. So we get e to the naught, which is 1, and we get kT. So the average energy for a continuous is kT. And what happened when he did that? Well, he was wrong, basically, is the answer to that question. But we'll say this was our blackbody curve looking something like this. His thing fitted these values here, but it kind of went off like that, and as a result was called the ultraviolet catastrophe. I think that's how you spell catastrophe. Alright, so that's all I've got to say about that. Thanks for watching. Please pass it on to your friends and subscribe to my channel.